Let us do this exercise. After it, we will then do this one. So we will use superposition to calculate the currents across this resistor, and this resistor. We will then calculate the voltages. Then after that, we will come to that one. Again, if you are at college and you are doing N4, in most cases, you will be asked to calculate the current across this resistor. They won't ask you to calculate the current across this one and this one. But in case they ask you, you must know what to do. Okay. I'm not gonna draw another circuit. This is what I'm just gonna do. We know that on superposition, the first thing we do is we short the first cell. We short the other cell and work with the first cell. So we will treat this circuit as if, we will treat the cell, yes, the cell as if it's not here. So when the cell is not here, we have this resistor, we have this resistor here. So let us calculate the total resistance across this parallel circuit, then add it to this resistor, which is now in series with that one. So let's write the formula for the total resistance. It will be R1, the resistor in series, plus R parallel. Remember, R parallel is gonna be represented by R. That's R load, times R2 divided by RL plus R2. So R1 is 8 ohms plus 8 ohms times 15 divided by 8 plus 15. So what we should have written there, we have short V2. So what is let's write this here. We say plus, then we'll say 8 times 15 divided by 8 plus 15. Our total resistance is 13,217 ohms. Now that we know the total resistance, we then calculate the total current, which is the current across this resistor. It's gonna be calculated by 5 divided by 13,217. Then our total current tends to be 5 divided by 13 is gonna be 0,1. Let's check. The total current is 0,378 amperes. So knowing the total current helps us knowing the volt drop across R1. So let's calculate that volt drop across R1. It's gonna be the product of current and resistance. It's gonna be 8 times 0,378. So 0,378 times 8 is equal to 3,024 volts. Knowing this voltage helps us to calculate the voltage across the parallel, which will be V1 minus VR1. Then this tends to be V1 is 5 volts minus this one which is 3,024. Then 5 minus 3,024 is equal to 1,976 volts. So with this voltage, we can then calculate the current across this resistor and this resistor. But since we want the current across this resistor, first, as I said, they always say calculate this resistor on N4. This is what you will do. You will say the current across RL is equal to this resistor, this voltage, which is the voltage across the parallel, divided by 8. This is 1,976 divided by 8 is equal to 0,247A. You would then stop here, short, calculate everything that we've calculated for this circuit. But now, because we said we will calculate everything, our calculations continue. So now we know the current across that resistor is the total current. This resistor is this one. So let's calculate the current across R2. It's gonna be 1,976 divided by the resistance across R2. When we add this current, we should be getting the total current. So 1,976 divided by 15 is equal to 0,132. You can see when you add, that's 9, that's 7, that's 3. So you get it. You get 0,3. Though this one is not, it's gonna be 7. Yeah, 7. So you get 0,37 instead of 8. It's 9, but it's almost the same thing. So our currents are balancing. So after calculating the currents, we are done, because we know the voltage and we know the voltages. We know voltages everywhere. Let us now short this one. And keep this resistor, which is 8 ohms. So we pretend as if this one is not here, this one. So these one are now in parallel. So let's calculate the total resistance. Which resistor is now in series is this one, 15 ohms. So it's gonna be 15 plus 8 times 8 divided by 8 plus 8. So let's punch that in a calculator. Plus 8 times 8 divided by 8 plus 8. This is equal to 19 ohms. So let's calculate the total current of the circuit. We will take this voltage, which is 10 divided by 19, and the total current will be 10 divided by 19, which is 0,526 amperes. This helps us to calculate the volt drop across R2, which will be the product of current and the resistance times 15. So let's just say times 15 here. 15 times 0,526, something happened that I don't trust. That is why I'm punching this again. this is gonna be 7,889. Whenever you calculate the volt drop here and it becomes bigger than this one, you must know that you have made a mistake. So let's now calculate the volt drop across the parallel. We know that it will be the same here and there. We're just gonna take 10 and subtract 7,89. Let's just say we'll ignore the sign there. So the voltage across the parallel is 2,11 volts. So now we can get the current across this resistor, which is the current that we are very worried about. Current across the load resistor. Oh, here we should have written also that we have shorted V1. Current across the load resistor will be 2,1 divided by 8, because the load resistor is 8. 2,11 divided by 8 is equal to 0,264 amperes. We would then stop if we are only asked to calculate that current. Take these currents and add them. The reason is, when these batteries are like this, we definitely know that when we short this one, electrons will flow this direction. So the direction of the current will be up on RL. And again, when we short this one, we've got negative here. Electrons flow this direction. The direction for the electron flow will still be up. So we will be adding these currents to get the current that we are asked to calculate for this circuit. But now let us let us consider the current for which resistor that we don't know now. Is this one, which is R1. I over R1. That one is the same as I over R2. R1, we know that this resistor is across the parallel also. So, these currents will be the same because these resistors are resistors of the same value. So 264. Are we getting that 5 when we add these? If we add this one and this one, we get 8. If we add this one and this one, we get 12. So we write 2. Wow. And we carry 1, 2, 2, 5. Then we get that one. Though it's not 6, it's 8. Doesn't matter that much. What else should we do now? We know the voltages, we know the current. So let us now calculate when we have both cells. So we said we're starting with the current across the load resistor. We saw that the direction is the same. So we're just going to take this 0,247 and add with this 0,264. We then get 0,247 plus 0,264 is equal to 0,511 amperes. So now let's come to the current across R1. When we shorted this one, electrons flow this direction across R1. So the direction is down. So what do we know here? We know that the direction is down. Now let us come to R1 here. When we have shorted here, R1 was here, an electron flow this direction and across this one up, across this one up. So what is happening here? The current flow is on the different direction. So what we must do is we will say for us to get the current across R1, we take this 0,378 and we minus this one, which is 0,264. So 0,378 minus 0,264 is gonna be equal to 0,114 amperes. Let's now come again to IR2, which is that resistor. When we shorted here, what was happening to that resistor? Current this direction, current goes this direction up and it goes up, so our current was going up. When we shorted this cell, what was happening across R2? R2 current was going down, so the direction of the electrons on R2 now was down. So the directions differ when we want the current across R2. So which one is bigger? That one. So we're gonna take that one, 2, 6, and subtract this one, 3, 2. So 0,526 minus 0,132 is equal to 0,394 amperes. So we got the current for both, but what about the voltages? The voltages, every voltage that we calculated was not for both circuits. So let's come here to the voltage across R1. So when we shorted here, what was happening here? This resistor was negative there, then positive to this side. So if electrons flow this direction, so this makes this one negative here and makes this one negative here, then positive that side, positive that side. So we can now calculate, okay, let me use this one now. This one will represent the polarity when we have shorted this one. The blue pen represented the polarity when we shorted V2. So when we shorted V1, this one was negative, this one positive, and then electrons were flowing this direction, so across this one, negative, across that one, positive. So across this one, negative, across this one, positive. So let's calculate the voltages, taking into consideration the polarities now. Which one we should start with? Let's start with the voltage across R1. So the voltage across R1, we saw that when we shorted that one, the polarity was negative on top and positive down. But now what happened when we shorted this one? The polarity was now the vice versa. So that means we are subtracting. So where is VR1? Is here. And where is VR1? This side. VR1 is here because R1 was now parallel. So these voltages are minusing to give us the voltage across R1 when we are using both cells. So it's gonna be 30,24 minus 2,11, which is equal to 3,024 minus 2,11 is equal to 0,914 ampere, volts. So let's come to the voltage across R load. So R load, across R load, when the polarity is the same, negative, negative, positive, positive. So that means across R load was parallel all the time, right? So R load, the voltage across R load when we shorted was 1,976. When we shorted this one, this resistor was now parallel to this one. So R load was always parallel. So we will take that one, 2,11. Then we add these voltages, 2,11 plus 1,976 is equal to 4,086. So let's go and calculate the voltage across VR3. So we noticed that, VR2. We noticed that when we shorted here, the polarity was like this. And when we shorted this side, the polarity was like this. So the polarity is the vice versa. So now let us come here and figure when we shorted that side, VR2, since this resistor was parallel to this one, will be equal to this voltage. And when we shorted this side, VR2 was now in series with these resistors, not in parallel. So that means the VR2 will be that one. So since the polarity is not the same, so we take that one, then we minus. So 7,89 minus 1,976. Then 7,89 minus 1,976 is equal to 5,914. So we did manage to get these voltages and the currents. So across the load resistor, let's check if we divide this voltage with that resistor, which is 8, what do we get? 4,086 divided by 8 is equal to 0.51. We get that current, so we balanced. Let's check if we take this voltage 0.914, then we divide this with R1, which is 8. What we get that current exactly as it is. If we take this one 5.914, we divide by R2, R2 is 15, we get this current. So I am convinced that I'm right.